the first place, I would like to say hello and to thank all the organizers, to Professor Mohamed Saidi, Professor Sass, and Othman for their kind invitation to this conference. It's for me an honor to give you this talk, which, as you can see in the title, is probably a little off topic from this conference. I'm going to speak about something which is probably very strange for you. I'm going to speak about metamaterials and metalenses, not so much on communications and so on. But in any case, I will try to give you some ideas that could be hopefully fruitful for your future research. So probably I will try to give you hints about communications and so on. And you can see in my title that I will speak about metalenses, not metamaterials, because I will not have time. So I will focus on metalenses. And at terahertz frequencies, which is an emerging range, which is now very important for electromagnetics research. As Professor Mohamed Saidi said, I'm Miguel Beruete, and I belong to the Public University of Navarra in North Spain. But of course, I didn't do this work myself alone. Let me give some credit to my colleagues, and especially I want to have a very special memory for my former professor and a very good friend, by the way, Professor Mario Sorolla, who passed away 4 years ago, or almost 4 years ago. So it was a great loss. So I always try to give him all the credit, because without him, I wouldn't be here, that's for sure. Also to Dr. Igor Campillo, who is now the University of the Basque Country. He was a good friend and a good collaborator at the beginning of my career. Professor Neider, very well known in metamaterials. Some of the results I will show you have been done in collaboration with him. Dr. Miguel Navarra, he was a former student with me. Now he's doing a brilliant research career at the University of Birmingham in the UK. And of course, last but not least, my doctorate students. They are doing all the heavy work, and I think it's just worth mentioning, it's just fair mentioning them here. Victor Torres, Victor Pacheco, and Bakhtiar Orazbayev. Well, here is the outline of my talk. First, I will start with some introduction to terahertz to tell you how important terahertz is becoming and why we should pay attention to this emerging frequency range. Then I will tell you about metamaterials, just basics of metamaterials. For those of you who don't know about metamaterials, I will give you some information about what they are not, what they are useful for, some history about them. And then I will concentrate on metalenses using mainly two technologies: fishnet metalenses, I will explain you about this later, and epsilon-near-zero metalenses that we have been able to develop. And finally, very short conclusion. So let me just start with terahertz technology. Well, where is terahertz and why terahertz? Why is it important? Well, terahertz is located just in the middle of everything. It's in the middle of microwaves here and infrared. So it's in the middle of two very mature frequency regimes. You can have, of course, you know very much about this. There are many applications in microwaves. You have mobile phones, you have, Bluetooth, you have many applications. So this is very well developed. In fact, microwaves, we have electronics in general. And everybody has electronics in their normal lives. So this is very well developed. And the same for the high frequency range, where there is now this, the equivalent of electronics, but with photons, what we call photonics. And there is also fiber optic communications and, remote control, like these lasers, for instance. And in the middle, we had this gap, the terahertz gap. And this was a gap because it was difficult to produce these waves and to detect these waves efficiently. In fact, we needed very expensive equipment to do this. But there has been, in the last few years, a series of groundbreaking discoveries that have helped to develop this new frequency regime, and now the opportunities are emerging very much, and very fast, in fact, because there are many people working together to develop terahertz technology. I'm sure that all of you now are familiar with this application here, the see-through closed radar that you can find at airports, for instance. You enter into a cabin, something like a place where only you can be there, and then they scan you to find if you have something below your clothes. And this is very important for terahertz because this is non-ionizing radiation. This is not harmful. Compare this with X-rays, for instance, which is very bad to be radiated with this. In this case, we can see very fine details, Notice that the terahertz radiation has a wavelength of around 100 microns, even less. It can be even smaller. So we have good resolution, but at the same time with radiation which is not dangerous for for the human being. Also, there are other opportunities here in biomedical applications, and this is also very important because many macromolecules like proteins, amino acids, something like that, these kind of things that are very important for medicine, have a special fingerprint at the terahertz range. And this is the reason why many researchers are now trying to explore these applications of terahertz. In fact, myself, I'm trying to move towards this application right now. And of course, in astronomy, because you must be aware that almost half of the background radiation of the Big Bang is in the terahertz range. So this is a very old application of terahertz to explore the outer space with this kind of waves. So terahertz is important in these cases, but also for communications. Here you can see this is the trend that experts foresee in the communications for the future. Now there is a band which is emerging now at 60 gigas. All of you know this. This is a new standard which is being proposed for wireless local area networks. But also another one at 120 gigas, and everything is growing because we demand more bandwidth, we demand more speed, so we need always to increase the bandwidth, to increase the operation frequency of our devices, of our standards in general. So in the future, we can foresee something like this. Communications in space using terahertz. This is very important because one of the problems of terahertz is that the atmosphere has a strong absorption peaks in this frequency range. But in the space, we don't have atmosphere. We don't have air, we don't have oxygen, we don't have anything that can kill this radiation. And this, this is a niche for terahertz applications. This is a very serious application that is pursued with terahertz. Also, we can foresee 5G communications with terabit per second capability, for instance, or even wireless local area networks with the same terabit per second capability, even personal area networks, with very short range communication, but a very high speed communication, and also for military secure applications, because in this case, this absorption of the atmosphere is an advantage. It's not a problem anymore, because I can ensure that only the guy that needs to hear what I'm saying is going to hear that. Nobody is going to listen to what I say to this guy from another system, because these waves decay very fast. So these are some of the applications that we could foresee. And very important, there are two main ways to guide these waves. This is where I'm going to concentrate in the rest of the presentation. We could use, for instance, waveguides. There are many proposals right now. Dielectric waveguides like fiber optics, or even metallic waveguides like this one here, or even planar technology, which is being used. But I'm going to concentrate on this, on quasi-optics. This is the science of guiding waves without waveguides, but using, let's say, mirrors, lenses, and so on. This is what I'm going to do here. It's like, launching a laser ray and guiding it with mirrors and lenses and so on. And so I'm going to use here several lenses working at terahertz. And why metamaterials? Why are we going to do this in metamaterials? Because the reason is very simple. Terahertz is in the middle here, so we can use the latest advancements both from microwaves, metamaterials, and from photonics or infrared plasmonics. And this is a very good playground, the terahertz, because we can take advantage of all these ideas, and they work pretty well because it is in the middle. So this is the reason why I'm going to concentrate in the next slides in metalenses, lenses based on metamaterials working at terahertz. So let's go ahead. Metamaterials. What are metamaterials? I'm going to read the definition, and then I will explain you this in detail. They are artificially made materials which exhibit engineered electromagnetic properties that do not occur or may not be readily available in nature or in the constituent materials. This is just a definition. What does this mean? Well, a metamaterial, let me just say what is not a metamaterial. A metamaterial is not a mixture of substances, which we do, for instance, chemistry to get a brand new material. This is not. This is for material science. This is not what we do. Metamaterial is more similar to an architecture. Think about, for instance, a Meccano piece or a Lego piece, Lego toy with your kids are playing all the time. The piece by itself is just a brick. It's just a piece of plastic. But when you combine them all together, you can build beautiful things. You know, for instance, you can get a spaceship, you can get a castle, you can get a boat, everything. Everything that your imagination dictates can be built with these pieces. With metamaterials, we do more or less the same. We combine pieces to get a brand new material. But these characteristics of this material depends both on the constituents and also on the arrangement, much like the Meccano or the Lego piece. So to understand this better, let's look at nature. It's always the best way to understand what is going on in technology. In nature, when we model the materials or the substances from an electromagnetic point of view, what we do is to homogenize it. Think about when you were students. The teacher usually said, let's take a volume very small so that it can be considered infinitesimal, and I can differentiate, and I can integrate. But he said later, but not so small that I can isolate a single atom, because in that case, we are in quantum physics, in quantum electrodynamics. What we want to do is to have many atoms. It's very small, but large enough so that it has many, many atoms, so that we can homogenize. This is the key word here. We can homogenize, so that we can define these polarization and magnetization vectors which account for the electric and magnetic response of this material. And then we can define the constitutive relations and find this epsilon and mu, the electric permittivity, magnetic permeability, which account for the electric and magnetic response of this material. So this is what we do, exactly the same with metamaterials. Instead of having atoms, we have meta-atoms, like these metallic rings. We arrange them all together so that we can, in the end, define some effective parameters, effective permittivity, effective permeability, which is not the same as these meta-atoms. It's due to the arrangement of these meta-atoms, more or less like that. It's the same analogy as with nature. So the short history of metamaterials, in fact, is quite a long history right now. They were first proposed in 1968 by Veselago. It was just a kind of theoretical study. Nobody cared about this, let me tell you. It was, you know, forgotten very easily, and it was rescued 30 years later by Pendry. But in that time, he just wondered, what happens if I have a medium with both permittivity and permeability negative? What happens here? There are at least three possibilities. These media cannot exist because they violate some fundamental laws of physics, like, for instance, conservation of energy, or they can exist, but they are exactly the same as natural materials, or the third possibility, they can exist, but they are different. And he found that the correct answer is the third one. They can exist. They don't violate any physical law, but they are different to natural materials. In fact, what happens in these materials is that the phase velocity, a group velocity of a wave traveling inside them are antiparallel. This means that these materials have a negative refractive index, and this is quite exotic. In fact, no natural material has this property. Only with metamaterials we can access to negative values of the refractive index. And this leads to the well-known property of negative refraction. This is a picture, a very simple picture. What happens if I come from air, for instance, to a normal material? Say this is water, for instance. Well, we have, this is Snell's law, we have this incoming ray, this is the refracted ray, and as you can see, they cross the normal. But if I use a left-handed metamaterial, I use a negative index metamaterial, what I have is this situation here. By just applying Snell's law, we get what we call negative refraction. And Veselago noted that this was very important for lenses. And he found something like this. Conventional lenses, usually with this shape, this is a convex shape, these are usually convergent. But with metamaterials, they become divergent. And the opposite is also true. These lenses are usually divergent, but with metamaterials, due to this negative refraction, they become convergent. In fact, we can say that metamaterials open a brand new world for lenses. They are very important for lenses. You can see here that nature is very, limited in the lenses that we can obtain. If we want to convert a plane wave into a point, an image point, we need to use always a hyperbola here. This shape here is a hyperbola. And this is it. This is all. All natural materials have a refractive index larger than 1, so this is all we can do with nature. But with metamaterials, we open up many other possibilities. We can have refractive index between 0 and 1. We will have ellipses. We can have refractive index equal to 0. This is a very singular case. I will tell you about this later. We will have a circle. We can have between -1 and 0 another ellipse, but in this case it is concave ellipse, or parabolas, -1. I will speak about this now, and also with any less than -1, again, a hyperbola. So there are many new possibilities, okay? And we want to exploit them. So for the moment, these are just some examples of metamaterial lenses that have been developed. You can see that there are many, and of course, this is just a very small example of the things that we can do with metamaterials. Next, I'm going to speak about some metalenses that we have done using the fishnet metamaterial. So I'm going to explain first what the fishnet is so that you can understand. Well, it's very simple structure. You can see here, this is a schematic. The fishnet consists in simply stacking perforated plates with the property that the holes are very small, smaller than the wavelength, okay? So if we stack them with large periodicity, this is a dispersion diagram that we can calculate with a numerical simulator. With this periodicity, you can see something very interesting here. You see that the slope of this curve is positive. This means that the group velocity, which is exactly, this is the definition, is the slope of this curve is positive. And also the phase velocity, because the phase velocity is just omega over beta, omega over bt. So both are positive. Both have the same sign. But if I reduce the periodicity of this fishnet, you can see that the slope is less positive. Here is almost null. This is a very interesting case, by the way, but I won't explain this because it's a little difficult to explain. But here, notice that for small periodicities, the slope becomes negative. And this means that the phase velocity is still positive, but the group velocity is negative. This means that we have metamaterial performance. It's much clearer in the next animation. You can see it here. This is a metamaterial. This is metamaterial propagation. This is a negative refractive index that I mentioned before. What we have is a plane wave. This is only, by the way, it's only a unit cell. You have to imagine this with infinite holes occupying all the volume, okay? We have here an incoming wave which comes from the back. This is air. And it goes, of course, the energy goes from the back to the front. But inside this fishnet, we have this very strange phase advance. The phase fronts become negative. This means that the group velocity is positive, the energy goes forward, but the phase velocity is negative. The phase goes backwards. This is negative refractive index. So we have been able to synthesize this negative refractive index. Now we can use it to develop lenses. And this is the idea. First, we will do this. We will use a refractive index equal to -1, so we need a parabola from our calculation before. And this is what we do. Here you can see, this is a 2D simulation. And you can see here a plane wave which comes from above. And here at the focal position of the parabola, we get a clear power concentration. It's the same here. But notice what happens inside. The phase fronts go backwards. We have negative refraction. And it's working very well. I mean, this is very simple to design. Just a parabola, and then you get this focusing. In fact, it was so easy that we decided to fabricate it. First, we need to do these calculations. We have to identify the frequency where the refractive index is equal to -1, so that we can do our structure. So from the dispersion diagram, we calculate the index of refraction and find that it is exactly equal to -1 at this frequency, 53.5 gigas. Okay? So here is the whole structure in CST, Microwave Studio, and here are the simulation results for the H-plane and the A-plane. In both cases, you see there is a clear focus at the focal position, as we have designed. So we were really satisfied. We decided to fabricate it, and here is the photograph of the prototype. It's very beautiful, and this is also an advantage. It's nice to show. This lens is very nice, so, and it works very well. So what we did to characterize it is to put here at the focus an open-ended waveguide, because we need a point source. This is a point source, as the focus is very small. And to characterize the radiation, we place a horn antenna at almost 2 meters in the far field region of this lens, and we obtain here the radiation diagram in both principal planes, H and E plane. And here are the results. You can see here a clear main beam around 0 degrees, as we designed. And from these main beams, here is the cross polarization, is quite small, by the way. And from these peaks, we can calculate the directivity with this well-known formula from antennas. You know this very well. And then we obtain a pretty nice directivity of up to 29 dBs. So we are improving the radiation of an open-ended waveguide, which is a very simple source. By simply putting this lens, we can increase the directivity very much. Well, we can do more things. We can put back-to-back these Bl-concave lenses. And in this case, what we will have is a point source here and a point image at the output. And here are some measurements. First, we compare the transmission when we put only a single plate and when we put the lenses. And you can see here the improvement at the operation frequency. Next, we scan with this receiver the power distribution along the lens axis here at the operation frequency. And you can see here that we have a clear focus, as we expected. And now we have found the focus. We scan the power distribution in the 2 principal planes, and you can see here the outcome. There is a clear focus again, so things are working pretty well. But the problem of these kind of lenses is that they are really big. They are bulky. They are volumetric. So we wonder, how can we reduce the profile of these lenses? And we thought about applying the zoning principle. This is a very old principle. This is very well known in antennas community. It was proposed first by Fresnel, right? So it's from the 18th, 19th century. Okay, and he found that, well, given that this is very, very thick, so, but from an electromagnetic point of view, we only care about the phase difference to get focusing. So he said, okay, let's reduce the lens profile every time a 2 pi phase advance is produced, so that we can have, in fact, this stepped profile, which is much thinner. In fact, Fresnel lenses are typically used in lighthouses because they need very, very thick lenses. So in principle, they can reduce the profile by simply stepping the lens. And you can find them also for space applications like this one, the Nike Ajax tracking radar that is here. And here is the expression. I'm not going to go into details. So we apply this zoning technique to our lens, and we get this result, much thinner. In fact, the volume reduction is up to 60%. It's very, very, very thin. And we can use much less perforated layers to get exactly the same performance. You can see here that we didn't do a 3D lens. It's a cylindrical lens because it's much easier to fabricate. This is equivalent to a parabola, but a cylindrical parabola, not a spherical parabola. Okay? And in this case, we calculate again the dispersion diagram, and from it the refractive index. And you can see that we are operating at 56.7, where the refractive index is minus 0.25. And we did this because at -1, this structure is very dispersive, and we don't want to have so much dispersion. And here things are, you know, softer, smoother here, so it's better to operate there. Here are the construction lines, and you can see that we can, with our stepped approximation, we can follow very faithfully the profile needed for the lens. Okay, so this is what we have. We have an ellipse, by the way, because it is between -1 and 0. And here are some simulation results. Now the power enters from the back, and here you can see a clear focus. Notice that inside, it is still a backward wave, it is still backward because it has a negative sign, but you can see that it is almost in phase. Of course, because it is closer to 0. When the refractive index is exactly equal to 0, this means that the phase velocity is infinite, so everything is in phase. So here we are approaching this singularity, this condition. So almost in phase, but still backwards. You can see here a clear focus, but also side lobes. Of course, this is the price we pay for reducing the volume of the lens. This is unavoidable. We will always have this. We also fabricated this, and then we obtained the power distribution in terms of frequency and also at different positions in the lens axis. We just sweep this with this receiver, a point source, an open waveguide here, and then we obtain these curves here. This is simulation, this is measurement. You can see nice agreement. There is some ripple here, but this is due to the Fabry-Perot that we have here. And here is this cutting here. We can see that the lens was designed at 49.5 millimeters to have the focus here, and in the measurement, the focus is reduced and also is displaced a little, somewhat shifted to 46.5 millimeters, probably due to tolerances. But in any case, it's working pretty well. So next, we obtain this, the field distribution in this plane, in the XZ plane. Here is simulation, here experiment, again, good agreement. And from it, we can calculate the full width at half maximum. This means the resolution of this lens. And we find that in the simulation is 0.57 wavelengths, good resolution. In the experiment is 0.67 wavelengths, so it's working pretty well. And a very interesting application for lenses in antennas is to characterize them in a lens antenna system. And this is what we do here. We place the open-ended waveguide at the focus of the lens and then characterize the radiation diagram. And from it, we can calculate the gain. And here you can see the experimental curve. At the operation frequency, you get a gain of 12.3 dBs. It's smaller than the gain that we obtained before, of course, because this is a zone lens and it's working, it's not so optimal as the full parabolic lens. Anyway, it's interesting result because the volume is much smaller. So what can we do to improve this lens? Here I'm going to show you a very simple improvement, but which has strong consequences. The idea is quite interesting. It was done by one of my PhD students, and he found something very, very interesting. How can we extend the bandwidth of this lens? Well, we can do something which is very smart. In principle, the fishnet is dispersive, and this is usually a drawback. But we can convert this into an advantage, because this dispersion leads us to, for instance, choose these frequencies where we have different refractive indices, minus 0.78, minus 0.43, and then try to fit the same profile at these two different frequencies which have different refractive index. The idea is like as follows here. We have these construction lines, blue for one of the frequencies, the pink are for the other frequency, and you can see here that if we do things well, we can have the same profile that fits for both frequencies. So the same lens is going to work properly at these two different frequencies. And if this is true, then we can we can think that also in the middle is going to work well. If I have two frequencies where the lens is working well, probably in the middle it's also working well, so I have broadband operation. This is the main idea. So this is what we did. In order to check this, we calculated the root mean square error between the ideal profile and the stepped approximation of our lens. And you can see that here in this calculation, we get broadband performance. The error is very small in all these wavelengths, in all these frequencies, here, whereas the previous lens has a much larger error. The profile of the previous lens doesn't fit with these two frequencies. So this is the result. The single band lens, the one that I showed you before, has this enhancement here. It's very narrow band, but the new lens has this bandwidth here, which is much wider. It's working pretty well. Oh, I have to run, sorry. So I'll go quite fast here. So here are some results, analytical, simulation, experimental. I'll go just to some details. Here is the comparison at these two frequencies between analytical, simulation, and experimental. And I'm interested in showing you the directivity here for these two frequencies. In the experiment, we get a directivity of more than 15 dBs, which is pretty well, and it's working in all this frequency range. So, as I have to run probably, I will skip this because it will take me some time. I want to show you directly the latest results that we have with another technology. So I'm sorry, I don't have time. I want to show you this other family of lenses, epsilon-near-zero metamaterials, that we have done in collaboration with Professor Neider and Guetta. The idea is very simple. When you have a refractive index that tends to 0, then due to Snell's law, the output angle must be equal to 0. This means that the wave follows the profile. You can see here that the wave is following very well this profile. So we can increase the directivity, and this is what we do here. We can obtain epsilon-near-zero media in nature, or using waveguides at cutoff. This is the strategy that we are following here. The principle is very simple. Here is the propagation constant of a rectangular waveguide. When the frequency is almost the cutoff frequency, beta tends to infinite. Sorry, to 0. So the phase velocity tends to infinite, and we can emulate an epsilon-near-zero metamaterial. Sorry, I don't have time to give you details, but you have to believe me, it is possible to emulate epsilon-near-zero metamaterials with these waveguides. Here is what the effect that we have. We have everything inside the waveguide is in phase. Okay, we have a tunneling of the energy inside the waveguide. So here we will have a refractive index equal to 0. So we need a circle. And here is the lens that we fabricated. It's difficult to see. Here is the circular shape. It's difficult to see. Here there are many, many narrow waveguides. It's very difficult to see, but believe me, they are there. So when we measure it with these two different setups, we obtain this focus both in the experiment, in the simulation, and in the experiment. We get clear focus. And also, the directivity now is around 17.6 dBs. And finally, we can also do this experiment where we have this beam steering. By simply shifting the point stars along this axis here, we can steer the radiation, the main lobe of radiation at different angles. This is just another example of things that we can do, and here is the same with radiation diagrams. I wanted to show you this because it's the latest result that we have, and I think it is rather impressive. This is a graded index lens that is working at 600 gigahertz, so it's very, very small. The frequency is very, very high. So the principle is getting the phase difference by simply changing the shape of the waveguides inside so that we don't need any profile. It's just flat faces everywhere. So here is more or less the idea. We have this graded index distribution and get this focus here, the same here. Here, depending on the dimensions, we get this permittivity. I will not go into details, but let me show you the results. This is a drawing, and this is a photograph of the fabricated prototype. This is, notice the scale here. This is very small, so and still we have very nice shape. This is very difficult to fabricate. And here is the dimensions, so that you have an idea. We are speaking of 53 microns and a length of 1 millimeter. So very small, but very large, very, very thick, okay? And these are the results. Experiment and simulation, clear focus at the operation frequency, a little shifted in frequency, but still a clear focus here. And then when we compare simulation and experiment, we see that there is a focus. It comes closer to the lens in the experiment, but it still is working very well. And here is a comparison in the power distribution at the output, experiment and simulation. And here is the cutting at the operation frequency and at the focus. Very good agreement between simulation and experiment. All in all, we get again a power enhancement of 16.23 dBs. This is difficult to do at terahertz because materials are really lossy there. So we are very excited about this result. And the resolution of the lens in the X-plane is around 0.5 wavelengths in the Y plane is around 0.76 wavelengths. So I think this is my last slide. I had to run, sorry. I apologize again. The conclusions are very, very simple. I have shown you here several metamaterial lenses based on two different topologies, fishnet and epsilon-near-zero, and with different functionality. So thank you very much for your attention.